So what is sustainability? Sustainable? This fire? I think we understand that any one thing in isolation we could probably live with. It could even be a good thing. But sustainability, of course, is about what we all do, the choices we all make collectively. It's about how many Earths it would take if everybody in North America, if everybody in the world lived at the same standard of living that I do, if everybody built a fire like this. And that's what makes sustainability especially challenging. It's about what we all do together, and it's about collective action. So we talk about the challenges of sustainability, the challenges about us all working together. What do we really mean? I think there's three main points. And the first boils down to value. And we look at this guitar over here, what's its value? What's its value to you? Maybe you don't play the guitar, so it has no value to you. If you gave me $1,000, would I give you that guitar? This guitar has been with me for about 20 years, so I'd probably keep the guitar even if you gave me $1,000 for it. I paid $400 for that guitar back in 1991. And if you bought a similar guitar today, would it cost more? Would it cost less? Values change over time. Values are different to different people. You think about the difficulty valuing that guitar over here, and let's extend that analogy to what's around us. What's the value of this wood? What's the value of the trees? What's the value of a stable climate? These are tricky questions, and different people are going to have different answers. And if we think that maybe the air is not being taken care of, or the climate isn't being taken care of, or the water isn't being taken care of the way we want it to, and we can ask the question, well, why doesn't the market take care of it? And that's a very sort of common question to ask. Why doesn't the market take care of the environment? Well, the market's just us, right? It's a reflection of our values. So markets set prices and people set values. And the values we place on the environment are something we learn about in school, right? It's not the sort of everyday decision that we make that we don't think twice about. If I'm going to go out to dinner with my wife, maybe take a night off, we might decide to go to downtown Ann Arbor, go to a nice restaurant, maybe we're going to spend $60 on dinner. Or on another night, we're in a hurry and we throw something in the microwave and barely spend anything on dinner, maybe even skip the meal. These types of decisions come very naturally, very instinctually. But if I'm going to ride my bike to work for a commute, I'm going to live in a certain area that allows me to do that, well, these are very heady decisions. There are trade-offs associated with those decisions. And decisions about carbon dioxide and climate, these are things you learn about in school. Who would have ever imagined being born and expecting that the gas you exhale, CO2, would somehow lead to a warmer planet? Obviously, it's not because of people exhaling. It's about fires like this and maybe 9 billion people making fires like this. Metaphorically, of course, in their cars, with the electricity they use, etc. So the values we place on the environment are something we learn about in school. It's something that we need to be educated about. And it means that it's a challenge to address these questions, these sustainability questions. The third area is about the distribution of costs versus benefits. When I decide to build this fire, you can see emissions coming from the fire. These are emissions that everybody shares, right? Nobody's bottling these emissions up and bringing them and putting them back in my house for me and my wife and my children to enjoy all by ourselves. They're shared. And we tend to act differently in groups when we share things than when we own them individually. So for instance, imagine yourself being on a ranch, and you own a ranch, and you have cattle out on your ranch. Just picture for a moment how many cattle are out there on your ranch. Are there shoulder to shoulder to shoulder cattle? Well, if they could be, you'd make more money. But of course, you're imagining that they're spread out because they each need pasture, right? So you have in your mind, automatically, you figured the optimal number of cattle for your ranch. Well, now imagine instead of that plot of land being just yours, it's shared by 10 neighbors. Do you imagine the same amount of cattle being out there being shared? Of course not. Everybody brings their own cattle. And next thing you know, the area is overgrazed. Right? This is what's called the tragedy of the commons. And we tend to act differently when we share things than when we own them individually. Imagine that you're going out to lunch with a group of people, and there's two things on the menu. There's hamburger and there's pheasant. Hamburger costs $5 and pheasant costs $105. And everybody's paying their own way. And if you're a college student or somebody fresh out of school, you're probably getting the hamburger because you can't afford the pheasant. Everybody's paying their own way. Well, let's change the nature of the game a little bit, and let's add up the bill and divide by the number of people there. Do you think some people are getting pheasant now? We tend to make different decisions in groups than we do as individuals when we own them. Again, nobody's bottling up the emissions from this fire and just putting them back into my house for me, my wife, and my children to enjoy later. The emissions are being shared, so I maybe feel differently about this fire than I would if this fire were in my house. This is the challenge of sustainability. It's about what we do in groups relative to what we do as individuals. So if we act differently in groups as we do as individuals, we have to question how we treat things we might share. The air, the water, the land, we share these resources. And because we share them, we may, just like the pheasant, just like the cattle, we may tend to overconsume them. And that's the challenge of sustainability. So while climate change was a story of what we know and what we don't know, air pollution is really a story about what we can see and what we can't see. And one of the big differences between climate change and air pollution in general is that, we'd be hard pressed to imagine that, say, 50,000 people last year died prematurely from climate change in the US, or that in Europe maybe 300,000 people died prematurely due to climate change, or around the world 2 million people dying prematurely from climate changes. Hard to imagine that actually happened, but with air pollution, that's actually the story. And air pollution comes in many, many different forms. So particulate matter is one of the most obvious forms that we can actually see. So the effects of particulate matter might range from the benign to the dangerous. From the benign side, you might notice a fresh layer of snow in your backyard becomes dirty looking after a few days. Or in this area, you might notice the ability after a few days to scrape your finger on a windowsill or on a railing, and you notice that it's rather dusty, and that dust probably came from the air. The effects of that might be asthma in kids. It might be premature mortality in adults. Now, these are things we can see. Smog is another form of pollution that we can see. You might think of a brown, soupy air. I'll never forget the first time I visited my folks after they moved to Orange County in California. I looked around on the first day and I thought the surroundings just looked like another suburban area. Then it happened to rain that night. It was rather unusual for the area. Next day, suddenly you can see Los Angeles and you can see the mountains. That's obviously air pollution. And smog as an air pollutant comes from tailpipes. It comes from refueling your car at the gas station. You might smell some of that. It's called volatile organic compounds as you fill up your tank, or lighter fluid from your barbecue, or paint fumes. These fumes combine with products of combustion from industrial processes, from traffic, and create this smog. A large component of that smog is ozone. That's actually something we can't see, but also photochemical oxidants. Those are the constituents of smog that we can see. And smog can be, of course, very, very harmful as well. Some of the effects might be benign. You go out for a run and you notice your chest is somewhat tight, if you go for the run. Of course, smog can lead to cardiovascular stress as well and premature mortality. So, of course, ozone is one of the constituents of smog that we can't see. There are other pollutants, of course, that we can't see. Carbon monoxide is one that we might be familiar with. We all know not to run the engine of our car in the garage with the door shut, because carbon monoxide actually competes with oxygen for sites on hemoglobin, reducing oxygen distribution in the body, and can lead to a form of suffocation. So we've talked about air pollutants that we can see and those we can't see. It gets really interesting where the two come together. We can think about sulfur dioxide, so sulfur being emitted from combustion or industrial processes. And sulfur dioxide actually is fairly toxic. It's toxic to people, it's toxic to vegetation. When sulfur dioxide actually combines with particulate matter, you end up seeing, cardiovascular stress. You see hospital beds getting pretty busy and when you've got the combination of those two pollutants coming together. So the typical solution to the sulfur dioxide issue is to actually raise smokestacks. So you see very tall smokestacks. The old phrase goes, dilution is the solution to pollution. So if you raise a stack high enough, well, you won't notice the sulfur dioxide on the ground, and that's true. But what happens is over time, that sulfur dioxide becomes sulfate, SO4, and sulfuric acid, and that's where the acid rain issue comes from. So the acid rain is a little bit less of a human health issue than it is an issue for agriculture. It's certainly an issue for forests. It's an issue for lakes. Acid rain can travel over very large distances. So the sulfur emissions from Detroit might affect lakes in the Northeast, reducing their pH and affecting fish life in those regions. So sulfur dioxide becomes acid rain due to these tall stacks. So the solution to sulfur dioxide was to raise the stacks, and that obviously puts the sulfur dioxide high in the atmosphere. But you don't need tall stacks to get pollutants high up into the atmosphere. So very stable molecules, CFCs, which you might have heard of, get high up into the stratosphere, even above 40,000 feet, due to their stability. So CFCs come from refrigerants, and they were actually a solution to a problem as well. Back in the 1930s, refrigerants used to be explosive or smelly, harmful, dangerous, and CFCs were a solution. By being very stable and inexpensive molecules, allowed refrigeration to become far more widespread. But of course, as these molecules got into the sky, it turned out to be so stable that they would end up in the stratosphere. There they actually deplete ozone, and the problem with that, of course, while we don't like ozone on the ground as a constituent of smog, it's harmful to people and to agriculture and to forests. Up in the stratosphere, it actually protects us from UV rays, protecting us from skin cancer, protecting agriculture from UV as well. So CFCs are an example of a solution to one problem causing another problem. Now, there actually is a happy ending with CFCs. This is one of the examples where society has gotten together and has actually banned the use of CFCs, and is on a trajectory to eliminate the emission of ozone depleting chemicals. And it'd be wonderful to imagine another Clean Air Act in the future that actually eliminates things like smog, eliminates sulfur compounds and the other air pollutants that we've talked about, carbon monoxide. And engineers can do a lot to eliminate air pollution from engineering decisions, from design, as we're going to talk about a little bit later. Air pollution is thankfully one of those problems that can largely be reversible. Air is very abundant, so if we simply stop emitting the pollutants, over time the air will be clean again. And even that ozone hole, due to those chlorofluorocarbons, those CFCs, is beginning to repair itself. There are other issues like climate change that are much more difficult to reverse, or as we're going to see when we go upriver on the Huron, water pollution and water resources. This is a much more difficult problem to simply reverse. So we've moved upstream from Detroit now to the banks of the beautiful Huron River, a place adjacent to the Great Lakes, which have 21% of the world's fresh water, at least surface water. And it's a place where we don't usually think about water scarcity, right? Even in North America, we've got about, let's say about 8% of the world's population, and we have about, say, 15% of the world's fresh water. So that's both surface water and groundwater. But I think we all know that the story isn't just about quantity. And we could think about whether we'd let our kids swim in this water, or whether we'd let them drink it, or eat the fish out of it. This begs some questions about what is the quality of our water. It begs questions about what we're doing to protect our water resources for today and for future generations when we think about sustainability. It wasn't long ago when we talked about rivers being on fire, in the 1960s, sewage in our Great Lakes, and clearly we've come a long way in those dimensions. But it's a question, what quality of water do we need? what quantity of water do we need? Not every place in the world is as well endowed as we are with respect to the quantity of fresh water. We don't have to go much farther than the Southwest, where not long ago they were talking about pumping water from the Great Lakes just to have the availability. And there's a nexus between water quality and quantity, right? It doesn't take a lot of pollution to foul up a water that is scarce, right? Dilution is a solution to pollution. So if you've got pollution, just add water and eventually it'll be dilute enough. Well, that's certainly not going to do in places where water is scarce. And here in the U.S. we have technology and engineered systems that are in place to protect our water resources and the quality, but not everywhere in the world does. And we can look at a place like Asia where maybe they have 30% of the world's fresh water and 60% of the people. So places of high population density, places with a lot of industrial development and without the engineered controls that we might see here in North America. So what does sustainability mean for water? It means access, not just the physical availability, but a high quality water and a water that people have economic access to. And so when we think about the water that's just around us, it's probably cheaper to simply protect what we have than to develop new technologies to reclaim water that we've already spent and polluted. All right, so materials are really a story about now versus later. We have enough materials today to keep the economy running. As population grows, that might be a bit more of an issue. But we have economics to take care of us in large measure. As we run scarce on materials, we tend to look for more sources of materials. We tend to find them. Even in the case of oil, where we're consuming so much oil every day, we tend to go explore and find some more of it. So as the price goes up, we go out, we look for new sources, the price comes back down. Now, when things truly become scarce, the price goes up, stays up, then engineers are pretty good at finding alternatives, right? So sustainability, when it comes to materials, isn't just about running out of stuff. Actually, the issue is much more complex. It's about economics. How much do the materials cost? It's about going out and finding more material. And just because the material might be available on Earth doesn't mean it's available to us as engineers. It's maybe located in a part of the world where we don't have access to it. And we certainly know that materials have been a source of conflict around the world, whether it's oil in the Middle East or if it's maybe it's water in Africa. There have been conflicts over materials over the ages. So we could talk about oil today, or we could talk about conflicts over water today. Lithium of the future, we talk about electric vehicles, and there's a question about where the future of lithium is going to come from and whether there might be conflicts over that. So we can talk about now versus later. We can also talk about here versus there. We can talk about the toxicology of materials as well. We're surrounded by toxic materials, even in our cars. There have been reports on lead and antimony and bromine in our vehicles, pesticides. There's a concept called body burden, where you can basically take a sample of your hair, or they can take samples of breast milk, and you find all kinds of toxic materials in the human body. The question is whether that's going to be an issue or not. Known toxics, if you take lead, of course we know that's particularly toxic. But the question is, what are the effects and what doses? And that's largely an unknown. So when we think about materials, we can think about their availability, we can think about their toxicology, we can think about whether we have access to those materials, we can think about price, and we should also think about where we put materials at the end of their life. Nobody wants that landfill in their backyard, so siting of new landfills is an issue. We can't recycle everything, we can't remanufacture everything today, so we have a continuing need for landfills. And those landfills tend to be put in those regions that tend to be economically disadvantaged, those areas that tend to be poor. When we think about recycling, a lot of the electronics recycling, We see circuit boards being shipped overseas to low-income countries where they actually need the money. A lot of those materials being recycled and then shipped back over to the industrialized countries or used over there. So when it comes to materials, it's not just about running out of stuff. There are all these other issues that we need to consider. So we started off talking about the challenge of sustainability when we have shared resources. We tend to think differently in groups as we do as individuals. And we went through some of the challenges. We talked about air pollution, we talked about water pollution, we talked about climate change, we talked about materials. And moving forward now, the good news is that we've got solutions to all these problems. Engineering design can address each one of these issues. Materials conservation, recycling, remanufacturing, solutions for air pollution, solutions for water pollution. Hopefully as we move forward, we'll have a chance to discuss these solutions that are going on in engineering colleges all around the country and all around the globe. So the challenge is less about the availability of technology to solve some of the problems we've talked about, and a lot more to do with what happens when the rest of the world begins to develop in the way that we have here in the United States. So have you ever stopped to wonder, if everybody in the world lived at the standard of living that we do here in the United States, how many planets of resources that might take? I stopped to do that about 10 years ago, and actually you could do that yourself. Now there are websites where you can make these calculations, like myfootprint.org or what have you. But when I went and did this calculation, I was surprised to learn that if everybody in the world lived at the standard of living that I do, it would take about 6 planets of resources. And that's actually a pretty typical number. If you look at the average US citizen, that's about right. So we took some action. We began to use less energy, turn the thermostat down, drive less, maybe ride my bike to work, eat less, etc. And a few months ago, actually, I went and made that calculation again, and I was very pleased to find out that the burden, if everybody in the world lived at our current level of resource consumption, would be at about 3 planets. So we basically cut our burden in half, or our footprint in half. When I began to dig into the calculations, why exactly that was, I was actually surprised to learn it had very little to do with flying less and driving less, and although those things helped, what really made the difference was the fact that our family expanded. We went from 2 people in our family to about 5 people in our family. We've now got 2 daughters and a son that weren't in the previous calculation. And so our load, our burden, our resource consumption hasn't increased very much, but the family expanded, and therefore we went from about 6 planets to under 3. Now naturally these kids are going to grow up, they're going to have footprints of their own, and that actually begs the question, what happens when the rest of the world begins to develop? And we've seen population growth is actually rather robust right now. When I was born, there were about 4 billion people on the planet. Now there are about 7 billion. And we're on our way to about 9 billion. In the meantime, we see that not everybody, of course, lives at the standard of living that we do here in the U.S. So the last time the United Nations Development Program did an analysis, about 20% of the world's population was found to use about 90% of the resources. And the bottom 10 or 20% of the economic ladder were actually using only about 1% of the resources. So when we think about it, the reason things are sustainable for the moment are that not everybody in the world lives at the standard of living that we do. So the question is then, when the rest of the world develops and aims to achieve the standard of living that we have here in the United States, what's going to happen? And we can do some simple math to show that actually the current path that we're on is not sustainable. There are about 300 million people in the United States. Now, if the average U.S. citizen requires 6 planets of resources, if everybody lived at that standard of living, we can do some simple math. And instead of 6 planets, let's just say it's 3 planets. It'll make the math a little bit easier. So there's 300 million people in the U.S., and if everybody lived at the U.S. standard of living, it would require 3 planets of resources. So that's 1 planet per 100 million people. As we look at population growth, let's just look over the last year or so. It's now 2012. Over the last year, the world's population has grown by about 100 million people. So clearly we're not on a sustainable trajectory. Again, we come back to the good news. We've got technology to reduce our resource consumption, to reduce our pollution per unit of goods and services we produce. So we can break down the sustainability challenge into this simple equation. I equals P times A times T. So the I here is the environmental impact. These are the challenges we were talking about. The air pollution, the water pollution, climate change, materials consumption. Those are all impacts. And it doesn't matter which impact or all of them that we're talking about. That impact is equal to population, P, times affluence, A. Now, the affluence, we can talk about that in terms of being gross domestic product per person. So you can see if I talk about gross domestic product per person, I multiply by population, I've essentially got gross domestic product there. Now, the third letter T is technology. And we can talk about that as being the environmental impact per unit of goods and services we produce. So we can talk about the environmental impact per GDP. So if we multiply population times gross domestic product per person times environmental impact per unit GDP, environmental impact equals environmental impact. This is sometimes called the IPAT equation. Now let's look at what this equation means. Well, we've talked about population and the fact that it's increasing. And we've talked about affluence, not just today around the world, but in the future as well. And this is a term, obviously, we would like to see increasing. So when we multiply P times A, we know that we're going to have an increasing amount of impact. So if we want to address these sustainability challenges, really it's about T. It's about technology. It's about the environmental impact per unit goods and services we produce. That's a technology question. We have technology to reduce those environmental impacts. But it's not just a technology question. It is the degree to which that technology is deployed. We have solar panels, we have windmills, we've got electric cars. The question really is about why we don't use them. And so it's not just about designing the technology, but getting that technology into practice. And getting that technology into practice is an economic question, it's a social question, and it's an environmental question, which is why we often call this the triple bottom line. It's about environment, it's about people, and it's about the economy. So we'll call that the triple bottom line. You know, back in the 70s and 80s, we used to think, well, we've got an environmental problem, let's let the environmental engineers take care of it. You know, they will clean up the smokestacks, they'll clean up the pipes going into the river, and everything will be okay. But we realized in the 90s that, you know, maybe Ben Franklin was right. You know, an ounce of prevention would be worth a pound of cure. So we thought about pollution prevention. Let's get the manufacturing engineers involved to prevent the pollution in the first place. Then we realized, well, in the 2000s, you know, it'd be a lot easier to prevent pollution if we designed the products to avoid the pollution in the first place. So we got into design for environment. Here, you know, 2010 and beyond, we're thinking about sustainability. We're thinking about sustainable enterprise, not just the design of the technology, but the deployment of the technology and the regulatory systems and policies that can make that technology profitable. So when we think about sustainable design, we think about enterprise, we're thinking about triumphs, right? Sustainable design triumphs. Avoiding traps, avoiding trade-offs, and working our way towards triumphs, as we're going to talk about here moving forward. Traps, trade-offs, and triumphs are really all around us. Let's start by talking about what a trap is. A trap is a design or a system that's marketed or presented as being sustainable or good for the environment, but it's really not good for the environment at all. One example that comes to mind might be the example of ethanol-based fuels for vehicles. Ethanol, when it comes from corn, actually requires as much energy, if not more, to produce than your gallon of gasoline. And with respect to greenhouse gas emissions, it's basically a wash, or it could even be more than a gallon of gasoline. So when it comes to ethanol, it's really about it's all about where you get that ethanol from. So a triumph works for the triple bottom line. So it's some design, a product, an innovation, a service that works for business, it works for the environment, it works for people. So examples of this might be a flat screen monitor. You may remember the old days when we had cathode ray tubes on our desks with our computers, and nobody seemed to want them, but there was no alternative. And when you actually look at that technology, it was very energy consuming, it was full of toxic materials. Then these flat screens, these flat panel displays came around, and suddenly these monitors had a lot lower burden with respect to their toxics, less energy consumption, and they took off in the market. So it was a product that people actually wanted that was good for the environment in so many ways. Then, of course, we realized that they're affordable, and we could use more space on our computer desktops, and next thing you know, there's 2 or 3 screens on our desks. And that's actually the danger of a triumph, is overconsumption. So you've got a product, people want it, it's good for the environment, and next thing you know that it's being overconsumed. So while we look for triumphs in sustainable design, there's always that danger that it's overconsumed or it's a victim of its own success. So we think about other potential triumphs like LED lighting, which is coming online. I mean, today, an LED light bulb might cost you $20. In 10 years, maybe they'll cost less than a regular light bulb, or at least in the ballpark. And when that happens, given their efficiency, you'll have a solution that's good for economics. It'll be good for the environment due to its increased efficiency. Its ability to light large spaces with very little energy. And it'll be good for people too, because people want lighting. It's been said that lighting, we'd have a lot more lighting in the world if it were more efficient and more cost effective. So thinking about triumphs then, we could ask what other types of technologies would fit into that category. We talk about solar, we talk about wind. Now, today, these aren't exactly triumphs. They certainly haven't replaced fossil fuels to a great extent. They've been heavily subsidized. The hope is, as we use more of these technologies, they will become more affordable, they will take off. We started off by talking about ethanol as a trap. And as we think about solar, we think about wind, we think about the need for renewable electricity systems. There's a question about whether cellulosic ethanol, a new form, not ethanol based on corn, but ethanol based on switchgrass or other types of woody products that are generally wastes today. And if we could develop that technology where these waste biomass, cellulosic biomass, could actually be converted into electricity at an affordable rate, and we'd likely have a triumph coming down the road. So cellulosic biomass is an example of a closed-loop system. So if you think about growing switchgrass, that switchgrass needs carbon from the atmosphere. So it pulls carbon out of the atmosphere and becomes a fuel, and then we burn it, and then it goes back into the atmosphere. So closed-loop technologies actually have significant promise as triumphs. It's not just in the fuel sector. You can think about closed-loop manufacturing, remanufacturing. You think about cell phones from the 1990s. They weren't quite cell phones. They were suitcase phones and brick phones and satellite phones. And, those technologies now have become so miniaturized that they really can't get much smaller. You don't want a phone that's smaller than the size of your hand, for instance. So what it does is create an opportunity. If the technology were there, the systems were there, the supply chain incentives were there, you can imagine a phone that you actually keep over multiple generations, but after your 2-year contract expires, or even sooner if the technology is available, just open it up, change the processor, maybe you change the screen, maybe you change the battery, and you can actually conserve a lot of the material and a lot of the processing, manufacturing burden that went into that phone. So closed-loop manufacturing is another example of a potential triumph down the road. Thinking about materials. So it surprises people to think about aluminum as not being as recycled as generally perceived. So what I mean is, we think of our beverage cans being made out of aluminum, we recycle those. But actually, it turns out if you look at aluminum, it's only used in the economy about 3 times before it ends up in a landfill or somehow leaking out of the economy. So we could think about closed-loop material systems, more advanced recycling. So if we have a aluminum-intensive vehicle that gets very good fuel economy because it's light, today if you have an aluminum-intensive vehicle and you scrap it at the end of its life, basically that aluminum is going to be downgraded. Maybe it's going to become a casting for an engine. After that, it might escape the economy or might end up in a product before it escapes the economy. But in a future world where the incentives exist, Triumph might be an example of being able to convert a body-in-white aluminum-intensive vehicle into another aluminum-intensive vehicle, where the costs line up, the material lines up. So, of course, aluminum has a very significant greenhouse gas footprint and electricity footprint to create. So if you could close the loop on that material cycle, it would go a long way towards reducing environmental burden, both in production and in the use phase of a vehicle, given the lightweight potential of aluminum, the strength material of the material. Another thing is that Triumph doesn't need to be a product. Like I mentioned, it could be a service, it could be a policy. Think about a regulation that might allow businesses, power utilities to internalize some of the costs of greenhouse gas emissions, for instance, pollutant emissions, mercury emissions, what have you. And that sounds like increased costs, but there are also some operating cost benefits to renewable technologies. So if you think of solar electricity, and once you've got it in place and the sun's shining, the operating costs can be fairly low. Same goes for wind. I mean, there are maintenance costs, of course, but it's not like you have fuel costs. So a policy that might encourage, in a smart way, a renewable electricity future might also classify as a triumph. And one of the interesting things about traps, trade-offs, and triumphs is that they're dynamic. Definitions change over time, technologies change over time, and what might be a trap at one point might be a triumph at a later point. That's a song called Going Through the Motions by a band called the Miracles of Life. And, I think that the idea of going through the motions is really what is the crux of the sustainability challenge. So when we think about going through the motions and sustainability, the real question for us is whether we're going to keep doing things the way we are, or whether we're going to use our engineering talents to make a better life, not only for ourselves, but for future generations, so they're not at risk of not being able to live at the standards that we live today, to have access to resources, material resources, climate resources, air, water, with the same ease that we do today. So really what it means is, for the mechanical engineer, it means thinking about the types of energy systems and mobility systems that we have today, but re-envisioning them. Thinking system-wide, thinking about our friends on Central Campus and what they can bring to the table, not just to have the technology, but the context of that technology. If it's mobility, maybe it's not just about the cars, but it's about transportation. It's about multiple modes. It's about the future of our cities. If it's civil engineering, maybe we're thinking about buildings and their place. Thinking about much smarter buildings that use energy much more efficiently, that recover the water that those facilities use. If it's industrial processing and wastewater treatment, maybe it's future systems where we can take wastewater and we can treat that wastewater in a way that not only that it cleans the water, but it also produces energy and produces fertilizer. If it's the chemical engineer, it's new ways of producing energy carriers and batteries that will allow us to store energy from renewable sources when they, at times like night where we may not have that solar energy available to us, or when the wind isn't blowing. If it's the computer scientist, it's the software and the applications that enable all that. If it's the electrical engineer, it's about that computer that really doesn't require so much energy, those server farms that are really running lean. And it goes on and on from there. Engineering is about technology, and sustainability is about technology. So we as engineers not only have to design those technologies, but to do that with an eye for what society really needs, not just today, but in the future.